Okay, so the exercise on hydrological analysis using digital elevation models, DEMs. So this is an exercise that we run in conjunction with the GIS course SBG051. You've hopefully received instructions like this. If not, yeah, you can try and follow along this exercise, but it will be quite difficult. I'll begin by just looking at the concepts behind the analysis rather than the GIS. So let's start with looking at the hydrology. This is a very, very simplified version of hydrology. We're looking at basically the topography, the surface topography, very hard. There's no, the water does not infiltrate, does not go into the ground. It simply runs off on the surface. And then at some point, the water comes to a river. We have enough flow to call it a river. We have water flowing over the surface here, but this is ephemeral flow, we could say. And then once it reaches this, we have enough accumulated flow for it to build a river, what we would regard as being a river. Very, very simplified. This is obviously a section through, looking out from the side. If we look at this from above, what we have is a map here where these lines are our contour lines, 30 meters, 40 meters, 50 meters, and so on. And then the water flows downhill, so at right angles to the contour lines. And then at some point we get this river. There's enough accumulated flow to say this is where a river should be. Another thing to look at here is this black line going around here, which is named the watershed. This determines where water flows in a different direction. So a drop of water landing here would run off in this direction on that side of the watershed and in that direction on the other side of the watershed. So it delineates a boundary between two drainage basins. The area inside here is what we should call the drainage basin. Quite often the term watershed and drainage basin are used interchangeably, and indeed that's something that we will encounter when we come to the GIS analysis being done here. But the watershed, strictly speaking, should be the line going between delineating two different drainage basins. So that's the basic idea of water running off. How do we translate that into a GIS model, a digital model, if we like? So if we return to our profile, which if you remember, or the section that looked like this, very simple with a river in the bottom, and we'd have watersheds there. If we then digitize that, introduce our digital elevation model, where each of these columns represents one raster cell in the digital elevation model, and the height of these columns is the height of the elevation, the value in the cell. They're still squares in the model, but to visualize this from the side, we turn them into columns. And here we have our watershed lines marked in, and onto each cell we're going to add 1 unit of water, a drop of rain, a millimeter of rain over the whole square meter, or some unit. There's no defined unit. We can set that in a more advanced exercise, but we won't do that now. It's just a unit of water is landing on each cell. It comes down in one go, lands on the model. It then has to run off somewhere. And you can see that we're going downhill here and downhill there. So the water is going to run off in a particular direction. So we do an analysis to determine which direction will the water run off, where is it downhill. And the steepest gradient downhill is what we're after. So it would always go towards the steepest gradient downhill. So it runs off down that way here, and here it runs off down that way. The water runs off in these directions, and then it accumulates. As it runs off, it accumulates. So here we only had 1 unit of water landing on that cell from above. This cell is receiving water from this one, as well as water from above. So it has the water from above plus that one there. This cell is receiving water from above plus the 2 that are coming from there, which makes 3. And likewise we go down here, so we have 1 unit of water from above, and then 3 from up there, and so on until we reach the bottom, and then we have the water coming in from this side as well, and it accumulates down to a total value of 20 at the bottom. We still don't have a river. We've accumulated all this water at the bottom here. So we've said that the accumulated water flow in this cell is 20, and that one is 9, 10, 8, and 9 there. So we have this accumulated flow. Where is our river? We'll say it's there. We have to make a decision. We have to use some sort of logical condition that tells us where we have a river, and we need to match this up some way with that. Right, well, okay, if I set it to 8, then that gets really high. If I set it to 9, then we it sort of matches. That's a good match. That's the decision I make. Where accumulation is greater than or equal to 9, that is my river, or is a river. So that's how I've come to that decision. It doesn't match entirely the correct positioning of the river, but we have to accept this error in our model, and that's how we've done it. Now this was a simple two-dimensional model, as it were. Not quite, actually more like one-dimensional, but dimensions are a problem. So let's move on to how the computer is going to do it in our DEM. So we're going to use an algorithm called D8. It's got 8 directions, and for each cell we're going to have a height value, but that height value has to then be translated into a flow direction. Which way will a cell send its water? Because essentially that's the important point, not the actual elevation, just which way will the water flow from that cell. So we're going to need to change the value of this cell to something else, one of these directions around here. And if the water were to flow from here to the right, we will put in the value of 1. If it were to flow to this bottom right, we'll put in the value of 2 and going around. So if it was to flow upwards, we get a value of 64. So let's just look at that in example here. So here we have our very basic DEM. There are only 9 cells in this, and the water is going to flow down there. It's not going to flow to the right there because that is actually a lower value and it's a shorter distance, so it's steeper than flowing over to there. So it's going to flow downwards. And then if we go up to this, if it flows downwards, we need to set the value 4. So that cell, instead of being 17, is now 4. And then we continue with this analysis across the whole grid of our DEM, and we get flow direction. We can see which direction the water is flowing in all these cells. And then we accumulate. So none of these cells up here received any water from anywhere else except from above, so they just get a value of 1. Whereas this cell here, this is receiving from there and from there, so it gets a value of 3. This cell here is sending its water to that one, and only this cell is sending it to that one, so this gets a value of 2 here. So we accumulate a value of 2 there. We can then combine all of this accumulation into streams by saying, well, where we have a value greater than something, in this case 1, it's a stream. So all of these become streams, and the stream is actually built up, connected, using a slightly more advanced analysis that isn't part of the D8 algorithm, but is found in your GIS program. So that's the D8. There's one more concept we need to look at before we really get going, and that is the concept of sinks. A sink is simply somewhere where water will collect and not escape, according to the D8 model. This cannot handle water flowing uphill to escape. It always has to flow downhill, this D8 model. Therefore, we have problems with these areas called sinks. The water cannot get out and it just gets stuck. So we need to get rid of them. We could dig away aside a channel here. There is a possibility to do that in certain software. But what we're going to use is a simple tool called fill. We're just going to fill up the holes so that there is no sink anymore. The water can just flow over that surface and down. So that's something we need to do before we start on this analysis. We need to fill up the holes so that the water flow doesn't get stuck anywhere. Right, so that's the basic introduction to the concepts behind our analysis.